Hello everyone. In this lecture, we will be talking about chapter 3, models for software architecture. So we will go over the overview models of software architecture in this video. Software architecture is like the blueprint of a software system. Just like buildings, architecture defines its structure and how different rooms are connected. Software architecture does the same for the components of software system. It provides a high-level view of the entire system. Think of decomposition as breaking the system down into smaller parts or components. Composition is the opposite. It's about putting those parts together to create the full system. This process helps us understand how the software is built and how everything fits together. Um, there are different architecture styles. Architecture style refers to the specific design or patterns used in the architecture. Examples include client-server architecture, microservices, or layered architecture. It's like choosing between different types of building layouts, like the ranch-style house or a skyscraper. Quality attributes, these are features that describe how well the system performs. For example, is it secure? Is it fast? Quality attributes ensure that the system meets its non-functional requirement like security, performance, and usability. Every software system is made up of components that do specific tasks. For example, a login system is a component. The architecture also describes how these components connect and interact with each other. These connections allow different parts of the system to communicate and work together. Once the components and their connectors are defined, we need to figure out where they will be deployed. Deployment means assigning these components to actual machines or servers. So software architecture also includes details about which server will run which component, making sure everything works smoothly when deployed. The software architecture must follow both functional requirements, what the software should do, and the non-functional requirements, like how the software should perform. For instance, a functional requirement might be user should be able to log in, while a non-functional one might be the login process should take less than 2 seconds. Let's look over box line diagrams. Box line diagrams are a simple way to show the structure of a software system. Think of it as the map of different components, the boxes, and how they are connected, or that's lines. These are often used early in the development process to represent business concepts and processes. Each box represents a component and the lines show relationships. The lines might mean different things like a dependency, control flow, or data flow between components. If you see arrows, they indicate a direction or order in which things happen. UML diagrams go deeper than box line diagram by showing more details about the system structure and behavior. While box line diagrams are simple and intuitive, UML helps communicate more specific technical details. This diagram represents an online shopping system using a box line model. The box represents key components of the system, and the lines show how they interact. So, a customer interaction, the process begins with the customer browsing the catalog and adding items to the shopping cart. Once they are ready, they check out. After the customer checks out, the system performs three key tasks. It checks the customer's credit record to ensure payment is valid. It updates the inventory to reflect the purchased item. It notifies the shipping department to begin processing the order. Box line diagrams are great for showing business concepts. They help us understand how a business process works and its key elements. From this, we can move on to creating more detailed software models like UML diagrams. UML diagrams is or Unified Modeling Language, that's UML, is a popular tool used in software design. It's object-oriented, meaning it focuses on designing software around real-world objects, which makes it a powerful tool for representing complex systems. Architecture Description Language or ADL is another method used to describe software architecture, but it focuses more on formal description and semantic meaning. ADL helps ensure that the architecture is understood in a more structured and formal way. The 4+1 model. This helps us to understand both the functional and non-functional requirements of a software project by looking at the system from 5 different perspectives or views. The 5 views. Number one is logical view. The logical view focuses on identifying software modules, their boundaries, and how they interact. It helps us understand the system structure and usage scenarios by showing interfaces and connections to the external environment. Process view. The process view deals with how the software behaves at runtime. It covers non-functional requirements like performance, communication between modules, and how the system operates under different conditions. Development view. The development view organizes the software into manageable units based on the actual file or directory structure. This view helps developers understand how to implement and organize the code. The physical view focuses on the deployment infrastructure. It describes how the software is installed, where it runs, and how the system hardware and networking configurations are set up for delivery. It's like laying out the architecture of the hardware and network that supports the software. The user interface view or UI view specifies the look and feel of the system. It ensures that the system is user friendly and may also impact other views such as the logical view and process view by detecting how users interact with the system. And finally, all of these views are validated and tested through the scenario view. Scenarios represent different use cases and usage scenarios that run through all the views, ensuring that the system meets both functional and non-functional requirements in the real-world scenarios. Now let's look over module 3.2, UML for software architecture. UML or Unified Modeling Language is a graphical language used to visualize, specify, construct, and document different components of a software system. Think of it as a blueprint for building software. UML helps us create system blueprints that cover everything from business processes and system functions to more concrete detail like programming language structure, database schemas, and reusable software components. UML is a powerful tool in object-oriented analysis and its design. It provides various diagrams that help us analyze and model the system effectively. It's even better. What's even better that UML can also generate code skeletons, making development easier. UML is widely used as a guideline for software requirement analysis and design. It helps model the problem domain, showing us the key elements involved in the system. So identifying key architecture elements using UML, we can identify significant architecture elements such as classes and objects during the design phase. These are crucial in defining the structure and behavior of the software. Modeling behavior and interaction, UML describes the behavior and interactions among these elements, helping us understand how the system components work together. It also helps organize the software structure and specify any constraints or necessary attributes. UML provides several types of diagram. They can be grouped into two major categories, structural and behavioral diagrams. These categories help us understand different aspects of the software system. Structural diagrams describe the static structure of the system, showing how software elements like classes and components are organized. Example is a class diagram. This shows how hierarchy and relations between classes. Component diagrams that describe how the different parts of the system are connected. Now, deployment diagrams. These show how the software will be deployed on hardware. Then you have behavioral software architecture. Behavioral diagrams describe the dynamic behavior of the system, focusing on how objects interact and behave. Examples include object collaboration, how objects work together, interactive diagrams showing the flow and messages between objects, and activity diagram describing the workflow and tasks within the system. So these are some static structural diagrams like class, object, composite structure, component, package, and deployment diagrams. We also have dynamic diagrams like use case diagram, activity diagram, state machine diagram, sequence diagram, interaction overview, communication, and time sequence. We will look into these diagrams in details in our next videos or next slides. Let's dig more into the UML diagrams. In addition to the structural and behavioral diagrams, UML offers several other important diagrams, such as sequence diagrams. These shows the order of interaction between objects. Collaboration diagrams focuses on the relationship and interactions between objects. And activity diagram. These describe workflows and the flow of control in a system. There are many UML IDE tools available. IDE is Integrated Development Environment. These tools are available that help in creating and managing UML diagrams. Some of these tools are open source, while others are commercial. Popular tools, some of the most widely used UML tools are Rational, Rose, Borland Together, or Microsoft Visio. These tools not only help in designing UML diagrams, but also support code generation, meaning they can map UML diagrams directly into popular programming language like C++, C Sharp, and Java. Class diagram provides a static view of the system and captures the vocabulary of the system being designed. It's the foundation diagram in the system design and one of the most frequently used UML diagrams. Class diagrams can be created by analyzing use case diagrams or through text analysis to identify key objects and their relationships. Class diagrams are initially generated by system analysts and designers. They are refined iteratively throughout the different phases of software development lifecycle, helping to further define and clarify the system structure. Each class in a class diagram is described with important details such as type, interface, properties, and methods. This helps define the structure and behavior of the class. One key aspect to the class diagram is the use of accessibility modifiers to control access to the class members. Popular modifiers include private, public, protected, and default. Class interface, an important part of class diagram in the interface. A class interface defines the behavioral contracts that class must support. It specifies what methods a class must implement without showing how they are implemented. This is crucial for ensuring different classes interact in a predictable and consistent way. In UML, there are three main types of relationship between classes. Inheritance, this is shown with a hollow triangle arrow and represents a parent-child relationship where one class inherits properties and behaviors from another. Aggregation, this uses a hollow diamond arrow and represents a relationship where one class is part of another but can exist independently. And association is the simply line without arrows and represents a general connection between two classes. Multiplicity defines how many instances of one class can be associated with instances of another class. Some typical multiplicity types include one-to-one. Each instance of a class is associated with exactly one instance of another class. One-to-many. One instance of a class can be associated with multiple instances of another class. And many-to-many. Many instances of one class can be associated with many instances of another class. In UML, multiplicities are denoted with specific symbols. 1 represents one instance, 0 represents zero, no instance, 1 dot 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 1 represents 0 or one instance, and 1 dot 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 star represents at least one instance. This diagram shows the logical structure of a purchase order system, which consists of 6 classes. Each classes have a specific role in the system, and there are different types of relationship among them. Inheritance, aggregation, and association. The customer class is the base class for both new and existing customers. This relationship is modeled using inheritance, where new and existing customers share common features but may also have unique attributes. Placing order, a customer can place 0 or more orders. This is shown as an association relationship between the customer and order class, meaning multiple orders can be linked to a single customer. Each order consists of multiple item lines, which in turn contain items. The relationship is represented as aggregation, where item lines and items are part of the order but can exist independently. In this system, inheritance helps categorize customers, while aggregation, association defines how orders and items are related. This diagram provides a clear view of how different classes work together to fulfill the purchase order process. A class diagram is not static. It can be refined and updated throughout the software development lifecycle. As the system evolves, so do its components, and the class diagram helps keep track of these changes. Several other UML diagrams can be derived directly from the class diagram. This shows specific instances of classes at a particular moment in time, that is object diagram. Component structure diagram, they provide a detailed view of the physical structure of the system, focusing on components and their relationships. Dynamic behavioral diagrams, such as sequence diagrams or communication or collaboration diagrams, are also based on the class diagram. They provide insight into how objects interact over time and how communication flows between them. Objects are actual instances of classes. Think of a class as a blueprint, and objects as the real world example that follow that blueprint. An object diagram provides a snapshot of a system at a specific point in time. It describes a sample subset of objects and their connections at runtime. Essentially, it's concrete representation of a class diagram, but focuses on actual objects instead of the abstract classes. The object diagram is derived directly from the preceding class diagram. It shows how class instances or objects interact and are connected in real-world scenarios. It captures a moment in time where the system is running, providing valuable insight into the system's current state. Behavioral diagram, such as sequence diagram, communication diagram, and interaction diagram, often refer to the object diagram to show how actual objects interact over time. They provide a dynamic view of the system, focusing on object interactions. The object diagram derived from the class diagram of the purchase order system gives us a clear snapshot of how objects are related at a specific point in time. Each rectangular box in the diagram represents an object, which is an instance of a class. In this example, the object diagram shows that the customer with identification number 1234 has placed an order. The order contains items, a book, and a gift. This snapshot helps us understand the classes, customer order, and items interact with physical scenarios. A composite structure diagram is used to describe how elements are connected and how they collaborate at runtime. It focuses on the internal structure of a system, or system shows how the different elements interact with one another. There are two key notations in the composite structure diagram. Represented by the dashed ellipses is collaboration. It shows how different elements work together or collaborate to perform specific tasks. And a rectangular box represented by the structured class. It shows the initial structure of a class, including how its parts are interconnected. In the composite structure diagram, each structure class can have an annotation that indicates its role in the collaboration. This helps clarify the part each class plays an overall process. For instance, the order processing collaboration, two classes are involved. The customer class plays the role of the buyer, and the order processing system class plays the role of a seller. Importantly, the order process itself is not a class or an object. It represents a collaboration between these two roles. The component diagram. So a component is not the same as class or an object. Instead, it's a deployable, reusable building block used in software design and development. Components are key elements in building large modular systems. Each component has an interface that exposes its service to the outside world while hiding its internal implementations. This interface acts as a contract between the reusable component and its client, defining that the component can do without revealing how it does it. The component diagram shows the structure of a shopping cart application. In the diagram, the cart component plays a central role, providing services to the front-end graphical user interface, such as ASP, JSP, or PHP web pages. The cart component is responsible for managing the shopping cart and providing services to the front-end pages. These services include adding items to the cart, updating quantities, and calculating total for the checkout. The cart component also relies on service from other components to function properly. like catalog component to retrieve product details, inventory component to check stock availability, shipping component to calculate shipping costs, credit check component to verify payment details. UML 2 introduced a new intuitive way to represent components and their connections. This updated notation helps developer clearly understand the relationship between different components in a system. The lollipop shape represents an implemented interface. This shows that the component provides certain service that can be used by other components. The cup shape represents a required interface, indicating that the component relies on services provided by other components. In other words, the component cannot function properly unless its dependencies are met. These interfaces enable seamless collaboration between different components, which are designed and developed by teams working on the project. By clearly representing both provided and required interfaces, this notation makes it easier to design modular, reusable components. The component diagram represents a clinic system and shows four main components: clinic component, billing component, patient component, and doctor component. The clinic component plays a key role in managing appointments and schedules. It provides the following services, which are represented as interfaces. Make appointment by patient allows patients to schedule new appointment with the clinic. Update appointment by patient enables patients to modify or reschedule existing appointments. Update schedule by doctor allows doctors to update their availability or schedule changes in the system. So the component interaction, each of these components works together within the system, with the clinic component acting as the hub for managing appointments and schedules while collaborating with the patient and doctor components. The billing component may interact with these services to handle payments related to appointments. In UML, a package is represented by a tabbed folder icon. It acts as a container for grouping together related classes and subpackages. This is similar to how the directories are used to organize files in a file system. A package helps organize closely related classes in one container. This makes the system easier to manage and understand, especially in large projects, by keeping related elements together in one place. By grouping classes into packages, we can better organize the system's structure, making it more modular and easier to maintain. For example, all classes related to billing or appointment in the healthcare system can be placed in separate packages. A package diagram shows the dependency relationship between packages. In other words, it illustrates how changing one package might impact other packages. This is essential in understanding the ripple effect of changes within a system. A package diagram also specifies the contents of a package. It shows the class that makes up each package and their relationships. This helps clarify how classes are grouped together within a package and how they relate to each other. Using package diagram to represent the system structure helps reduce dependency complexity. By organizing related classes into packages, we simplify the relationship between large group of classes, making it easier to manage and maintain the system. So in our next class, we will look into deployment diagram and some other key important diagrams like use case diagram.